Sir, hello.
Yeah.
Sir, you can start now. We are live.
Can I start now?
Yes, sir, you can start now.
Distinguished senior scientists, colleagues, and my young friends, good afternoon and welcome to the 6th live talk in the Ministry of Earth Sciences webinar series. At the outset, I would like to thank the Ministry of Earth Sciences and in particular IITM Pune for organizing this talk. And I am Ramadass. I am a scientist at National Institute of Ocean Technology. I am heading a group called Deep Sea Technologies Group. Today, I'll be talking about the development of technology for exploration and harvesting of the deep ocean minerals. I can see a few eyebrows rising about the word harvesting because we don't want to use the word exploitation. It has some wrong connotation, so we have used the word harvesting. And many scientists, engineers, administrators, and consultants, they did human service to this project of national importance since the day then Department of Ocean Development and now Minister of Earth Sciences, Government of India announced this project. And I can say that scientists from NIO, NIOT, and now NCPOR, they have spent a major part of their lives at sea, especially at Indian Ocean, for the sake of this project. What I'm going to talk about is a gist of their work. And so I start my talk by paying a very rich tributes to all these scientists who have contributed immensely to this field. In fact, the field of oceanography and ocean technology has received a major fillip during the execution of the project. With this introduction, I would like to go for my talk. So as you can see, today we'll be talking about the development of technology for the exploration and harvesting of the deep ocean minerals. And this is the outline of my talk. First, I'll be giving a brief history. Then I'll introduce you to deep ocean minerals. Then I will be talking about survey and sampling techniques. Then we will have a brief view of the world scenario on technology development. Then we will give you details of the Indian efforts as a part of the case study. And then a brief mention about the future work. And we will close the talk with the summary. And as you all know, the statement that 71% of the earth is covered by ocean is an oft repeated cliche. It may be a cliche, but it has a profound cliche. Because this 29% of the land that is available to us, you can see from the slide, 71% is habitable land and another 29% is covered by glaciers and barren land. Like that, if you see, hardly 1% of the land is using for mining. And we have been using the minerals from this land. We have been using, misusing, and abusing these minerals for last 5,000 years. And imagine if 1% can see us through for 5,000 years, then what can 70% give us? So that is the importance of the deep ocean mining concept. And as you can see from the slide, these minerals, terrestrial minerals, are highly unevenly distributed. It is ironical that the poorest continent has the richest of all of them. And this is the world scenario. As you can see, many of the minerals will not last even for some decades, and some may last for some centuries. And the great demand from the developing countries for their just share of and genuine needs, actually, it is increasing the demand for these minerals. Of course, we can alleviate these things by more exploration, better technology, and reclassification of resources to reserve. But there is a limit to what we can do about it. So the ocean mining is imminent. It's not the question of if, but when and how. So it's actually, this is the history. And in 1870 itself, there was speculation by Jules Verne, a famous science fiction writer, about the availability of these minerals at the sea bottom. but he said it is easier to exploit it. It's easier said than done, and we find it very difficult now. And as you can see in the right-hand side corner, that's a painting of HMS Challenger. During 1872 to 76, they sampled some polymetallic nodules, which are like potatoes strewn on the seafloor, and they found that they are rich in iron, cobalt, nickel, and manganese. So we can say that that is the beginning of the ocean mining efforts. And there is no unique way of classification of these ocean resources, but I can say that they can be living, non-living resources. In the non-living also, today we are going to concentrate only on the seabed minerals, because there are some dissolved minerals like salts, uranium, and other metals. But our concentration is on the seabed minerals like oil and natural gas, but I'm not going to talk much on them, and diamonds also I'm not going to talk. But gas hydrates, polymetallic nodules, cobalt crust, and polymetallic sulfides, actually, these are of our interest to the Ministry of Earth Sciences. So we will be concentrating on these four resources. As you can see, India has a exclusive economic zone which extends up to 200 nautical miles. Extended exclusive economic zone also extends even further also. So whatever is available here, it's actually our resources. We can use them without any permission, express permission from any other organization. But beyond that, actually, what is available, it's called high seas, and it is regulated by United Nations, especially by International Seabed Authority. It is an independent body, and they allot this one area for the exploration and exploitation of the minerals, and that area is called the area. And beyond, actually here the rights are only given for the seafloor, what is available on the seafloor, but the other waters above are called high seas, and we have no rights about that one. A portion of this profits from this mining, whenever it comes, actually, should be considered as common heritage to mankind, and it should be used for all the mankind. So where do these minerals occur? Starting from the continental slope and the continental rise, the first mineral that generally occurs is the gas hydrates. As the very name suggests, actually it is a hydrate which contains gas. It is like a camphor. It can be lighted, actually, and you can hold it also. A cage of water molecules, they host a gas molecule like methane or some other gas, actually. In our case, it's mainly the methane. A cubic meter of gas hydrate can comprise, actually, 163 cubic meters of gas. It's like a small gas cylinder. And as you can see from the map of India, along the continental margins of India, gas hydrates are available beyond 1,000 meters water depth and beyond 100 meters below the seafloor. It's estimated that even mere 15% of the world global, let me see if we can tap the gas hydrates, then next 200 years of the energy requirement can be met. Of course, we have to take it with a big pinch of salt. So Ministry of Earth Sciences has an exclusive program on these gas hydrates, especially in the Krishna Godavari basin. We have concentrated our efforts. The next one is polymetallic nodules. These polymetallic nodules are ferromanganese deposits. They actually look like potatoes, the size of maximum 10 centimeters. They are actually called two-dimensional minerals in the sense that they are available on the seafloor, and what all we have to do is that pick them up from that depths. But it's at 4,500 to 5,500 meters water depth, and these nodules, they grow very slowly, maybe 1 to 3 millimeters per million years, and that too when there is a nucleus like a sharp tooth or some kind of some hard rock or something like around that, layer by layer these things grow. And about India, actually, India has become a pioneer investor in 1997, even before the starting of this International Seabed Authority, along with few more nations. And an area of 1,50,000 square kilometers was given to India in the Indian Ocean, which is at almost 15 degrees south, 13 to 15 degrees south of India, from 2,400 kilometers away from the Indian coast. A 15 years contract has been signed with ISBA in 2002, and it was extended up to 2022 in 2017. And as you can see, the area is around 2,400 kilometers away from the Indian coast towards the south, and it has so many million metric tons of nodules which contain manganese, cobalt, nickel, and copper in the quantities mentioned on the right hand side. And you can see the percentage. Actually, manganese is 27 to 30%, copper is 1 to 2, like that and all. But it takes around 9 days for the ship to reach this place. Okay, as the old joke goes, by the time the ship reaches there and starts working, 50% of the team is seasick and the rest of the team is homesick. So next one is polymetallic sulfides. When the continental plates meet, when there are some gaps, the cold water tries to seep in and it meets the hot magma which is trying to come up. So when they meet, a geyser-like system forms, and the steam that is actually generated, it gushes out. While coming out, it brings a lot of metals in the form of sulfides and sulfates, especially iron, copper, and zinc. And these sediments close to the vent, they enrich the rocks around that one. It's called a mineralization. And these minerals can be harvested by using the right kind of technologies. And India has signed an agreement again with the International Seabed Authority for exploration license, a 15 years exploration license in 2016. This is even further. Actually, it is at around 25 to 26 degrees south, as you can see in the picture. And National Center for Polar and Ocean Research, MCPOR, under the aegis of MoES, they have started a mission mode multidisciplinary program, and they have done a lot of survey and sampling work at this place. And another important mineral is the cobalt crust. But cobalt crust is actually, it is very much similar to the nodules, but they are like layers stuck to the ocean bed. So we have to scrap it and take it. Actually, it's not exactly a 2D mineral, so it needs some kind of hard scrapping. So it generally occurs in the seamounts, and there are around 33,000 seamounts worldwide. In the map, you can see these areas marked are actually the seamounts. India has not yet signed any contract with the ISBA for exploration of this cobalt crust. So what are the challenges? Now minerals are available, but it's not as easy as actually terrestrial mining, because oceans, as we call it, inner space, is more difficult to conquer because it's a dynamic medium, and the hydrostatic pressure at 6,000 meters, actually the pressure is around 600 bar. So if you send a big vehicle there, it becomes a sort of a pulp at that pressures. So we need to develop appropriate technologies, pressure resistant, pressure compensated, and pressure tolerant technologies for that one. And density and salinity variations also pose problems. Temperature is at around 35 degrees on the surface and around 2 degrees centigrade at the bottom. Of course, corrosion, especially galvanic corrosion of different metals, is a serious problem. Another serious problem is electromagnetic radiation doesn't travel in water more than a few hundreds of meters, or if tens of meters, in fact. So you can control a Mars rover sitting on Earth, but you cannot control a machine that is operating on the seabed from the ship without a cable, because electromagnetic radiation doesn't even travel maybe beyond 100 meters. So we have to depend on the sound, which is 1 lakh times slower, and information that can be carried is very small using that one. And power sources and transmission, the power has to be transmitted from the top using a very long cable or using batteries with some limited capacity. And also the ship actually is not very stable at that depths, at that high seas. So we need specialized launching and recovery systems. So now we know we want to survey actually how these minerals are occurring and where they are occurring. So what do we do? So what we do is that there are different kind of survey techniques available to us actually. There are seismic techniques, acoustics, geophysical, and imaging techniques are also there. So you can see from here, actually this is a seismic survey, a typical seismic survey. Here, as the very name suggests, there is a source which generates shock waves in the ocean waters. So these waves travel down and they reflect and they refract at the different interfaces of the seabed. And seabed, there are layers below the seabed, sedimentary rock layers, impermeable rocks are there. So they get reflected and refracted. So by using hydrophones which are towed behind the mothership, we can receive these signals and analyze them, and we can detect some kind of minerals, especially oil and natural gas and gas hydrates. These seismic techniques are really not useful for polymetallic sulfides or polymetallic nodules, but they are actually an excellent survey technique for gas hydrates and oil and natural gas. Next comes acoustic survey systems, because we don't have luxury of using electromagnetic radiation. If you want to see Saturn rings or Jupiter satellites, you can go to your terrace with a good telescope and you can see them. But what is below in the water, if you want to see, you have to take a ship and you have to go to that area and you have to launch equipment which can go to the bottom. So in fact, in oceans, we use sound to see. So most of the equipment used there are actually acoustic based rather than electromagnetic based. Even the location of the object that you are placing on the seabed, it has to be found using acoustic techniques, which is similar to terrestrial GPS, because the GPS signal is not available at the bottom, sea bottom. So we have to use acoustics. So for the survey sake, we use sonar systems. There are umpteen number of sonar systems. There are different types actually, but for our survey, we can say that we use 3 different kinds of sonars. One is echo sounder, and another is a side scan sonar, and another is sub-bottom profiler. As you can see, a single beam echo sounder or sonar, it just sends a pulse below the ship. The sound pulse hits the bottom and comes back. We measure the time elapsed for the signal to go down and come back. And we know the velocity of sound in water, which is approximately 1500 meters per second. So then by multiplying the time and the velocity or speed, actually we can get the distance. So half of that one is the distance between the ship and the seabed, that is a depth. So as the very name suggests, the single beam sonar sends only one pulse. So you get only 1 point below that one. But in the big area, in the open ocean, covering large area is a difficult thing with the single beam sonar. So there is another way of doing it. It's called multi-beam sonar. 240 beams are radiated into the water. They cover the large swath of area at the bottom. When they come back, we can actually construct the bottom. You can see on the right hand side the difference in the detail we get when we use multi-beam sonar and a single beam sonar. And next one is side scan sonar. Side scan sonar is it's actually an imaging sonar. Actually, you can see what is there at the bottom. This kind of side scan sonars are used for finding the 2-dimensional minerals that are lying on the bottom, and they are also used for search and recovery and seeing the shipwrecks or lost aircraft and many other objects of interest on the seabed. And there are, of course, some kind of special kind of sonars which work on the backscattering. I'm sorry for the spelling mistake there. So the nodules, they scatter the incoming sound radiation, and by studying that backscatter, we can estimate the objects that are lying on the seabed. So far we have learnt about the survey techniques that can be used from the surface. But for 6,000 meters, if you want to really penetrate, you have to use a very long wavelength sound. The problem with using long wavelength sound is that you get very small resolution, very coarse resolution. Okay. So many of the details are lost when you do the survey from the top at 6,000 meters water depth. So what we have to do is that we have to take this equipment close to the seabed. For that, we need some kind of underwater vehicles. So the first one we generally use is called a DeepToe. As the name suggests, actually it is stowed behind a ship. It is hydrodynamically designed in such a way that it flies at a no given speed, it flies at a given depth below the sea surface. So a suite of sensors is actually fixed onto these things, and as we can tow the tow body behind the ship, you can collect a lot of information and data and even imagery, and either this can be transmitted online to the ship or it can be stored in the DeepToe itself. So this is a typical DeepToe used by Scripps Institute of Oceanography. And for taking visual pictures of the or video or still photographs at the bottom, this DeepToe have to fly very close to the sea surface, sea bottom. But sea bottom need not be always even. So especially in the places of hydrothermal vents and all, it's very hazardous to fly these systems just above the seabed. So the next system is a remotely operated vehicle. It's a robo which can go down, and there are variety of remotely operated vehicles based on the size and the function. So what we are typically showing here is a remotely operated vehicle, work class deep water remotely operated vehicle developed by NIOT. And the payload comprises sonars, lights, cameras, and sampling devices. Of course, actually at beyond a few hundred meters actually depth, that's pitch dark, so you have to carry your own lights for taking the images of the bottom and the objects that lie there. So, and these vehicles are also used for taking the sampling devices to the bottom. And the ROV has an umbilical that connects the ROV to the mother vessel. So you can see what it is doing. You can intervene, you can use the robotic arms, and you can do some kind of intervention. But the problem is that it's the distance it can move is limited by the cable, the length of the cable. If you use autonomous vehicle, which doesn't have any connection with the mothership, which is a self-propelled autonomous vehicle, then this problem is not there. You can have a wider reach. But the problem is that because of the lack of communication between the autonomous vehicle and the mothership, you don't know what it is doing. It is completely pre-programmed. It can fly in a way you program it, and it collects all the data that is intended to be collected. And you can see this data only after it is actually recovered. Maybe you can get some rudimentary communication using the acoustic data and all, but you cannot get any online control over this AUV from the mothership. So it is equipped with sonars, underwater cameras, altimeters, even magnetometers. So it is any sensor of interest can be interfaced with this AUV. So now we have done the survey from the surface. Then we have gone into the water column, and just above the seabed, we have made the survey using DeepToes, ROVs, AUVs, and all. Now we know what is there on the seabed. But how do you sample it? Unless you get to know what is lying there, what is the abundance, and what is the grade of the ore, whether it is worth really collecting this ore from the seabed, we need some kind of sampling. So there are different kinds of sampling devices called like graphs, dredges, and corals. And these things have been extensively used by National Institute of Oceanography, Goa, and now they have been used by NCP or Goa. And I'm just to give a feel of it, I'm mentioning only two grabs. One is Van Veen grab and another is a boomerang grab. As you can see from the picture, Van Veen grab has a scissor-like contraption, and there are two arms are there with some buckets. When this grab hits the bottom and a rope is pulled, it closes, and while closing, it actually traps some kind of nodules or minerals or sediments what are lying there. And so with the cable, actually you can pull it up and you can just collect the nodules or samples at the surface. The one you are seeing here, a boomerang grab, actually it doesn't have any cable. So it is launched with a buoy and a weight. So it goes down with the negative buoyancy and hits the bottom. When it hits the bottom, the grab closes and the weight is lost. So it collects some nodules or samples, and because of its positive buoyancy, it comes to the surface. When you take it up, actually you get the nodules. So you can estimate in a square meter on average how many kilograms of the minerals are available. And you can analyze these minerals and say whether they are of good grade, whether it's worth really proceeding further. And there are some other sampling devices called dredges actually. These are launched with a rope from the ship. They have a net behind this a metal ring. So it is weighted. It is literally dragged on the bottom. So when it is dragged, these samples and minerals, they get collected there. So it can be brought back and you can have the samples for analysis on the ship. And another one is corer. When you launch these things, actually with the weight, they go and they penetrate the bottom, and some core is actually trapped in the barrel, and you can bring it up and you can analyze that one. There are different kinds of corers, different variants are there. I'm only just showing only two varieties of them, and one is actually a gravity corer, and another is actually a box corer. The box corer is actually pushed into the bottom by the gravity force, and we get many times undisturbed samples of the bottom using this box corer. So now we know, actually we have got, first we have surveyed, then we have gone into the water, had a close look, and we have even sampled these things, and then we have estimated what is the grade of the ore. But now we have decided to at least mine them, at least by exploratory mining, if not for the commercial mining. Then we need some kind of underwater mining machines which can go and move on the sea bottom and collect the minerals available there. There are different types of mining vehicles. Different countries have used different kind of technologies. These can be broadly classified into self-propelled systems and towed systems. So as the name explains, towed system is actually, it doesn't have any self-propulsion. It has to be moved behind a ship. The problem with this system is that ship has to move. And if you have to cover a large area, ship has to make those movements. And it is actually very expensive and very time consuming, and it's really economically and technically, it's not a very efficient system. The other one is self-propelled system. So these systems, they move on the soft seabed. The seabed is so soft here at some places, especially in the polymetallic nodule sites. The bearing strength is hardly a few kilopascals. Shear strength is around maybe 2 kilopascals. So it is like grease. So we have to we have to size the machine, and we have to make its weight also appropriate so that it doesn't sink by its own weight on the sea bottom. So these self-propelled systems, they not only have to withstand that soft seabed, but they have to get some traction to move forward. So there are some tracked vehicles. It is like a military tank-like system is here for moving the vehicle forward. And there are something called Archimedes screw. Actually, when the screw moves, this vehicle moves forward. One of the most successful demonstration of underwater mining, that is actually Clomer Explorer, it used this kind of Archimedes screw for propelling. But there are still some people, like especially Japan and China, they are still trying to use these sleds for their own purposes. You can see this Korean institute called Kodi, actually, they use a self-propelled test miner. And the sea trial is done in 2009 and 2013. The maximum distance depth they have gone is 1300 meters. The next one is actually China. China has gone for this tracked vehicle. You can see with a track belt, it can propel forward. And whereas Japan has done some experiments with a towed miner system. So, okay, we have a mining system which can move on the sea bottom, but it has to collect the nodules or it has to collect the samples, especially when we are talking about the two-dimensional minerals like nodules and all. It is easy to collect these things, but we need some kind of collector systems with appropriate efficiencies. These collector systems can be passive, that means just you can see a collection system is attached to the mining machine. When the mining machine moves forward, then it plows through the that seabed and it collects the samples, and the water is actually, it is thrown out. But again, it's not a very efficient system because then it actually slows down the collection. There are some active collector mechanical mechanisms. You can see on the left-hand side, it is a typical potato harvesting machine. There are two trains, actually one moves and another is fixed. So what happens is the potato-like structures, they are picked up by this one and they are conveyed using a conveyor belt to the mining machine. The advantage of the system is that already the nodules are washed. So we bring very less amount of sediments when we use this kind of system. There is another variant of this one. This is a hydraulic lift system. In front of the collector, there is a nozzle and a high pressure water is actually sprayed here. It creates a low pressure area here and nodules are sucked into this one. This system is also, the efficiency of the or efficacy of the system has been well demonstrated recently by Japanese engineers while harvesting hydrothermal sulfides. So now we have collected the nodules also, let us say. Now the mining machine collects them, but how do you send it up to the mothership? How do you bring it up to the mothership? Let us remember that it is actually around 5,500 meters water depth. There are different kinds of techniques were tried. Some of them may look trivial now, but when they started, actually, they demonstrated these techniques. The first one is called continuous line bucket system. There are number of buckets. Actually, you can see for this we need 2 ships. So these buckets are circled actually between the ships and the sea bottom. So when they go down, they pick the nodules, they come up, it is emptied here, and again it is actually sent to the bottom. So it looks mechanically simple, but it is very complicated in implementation. At shallower depths, maybe this is a good idea, it can be used, and it has been used. But for deeper depths, it is very difficult. In fact, when they tried, these things got entangled, so this was later dropped. Another very innovative idea is that you can send autonomous underwater shuttles, or you can call them even drones. Okay, it can go down, collect these nodules from the mining machine, and with it drop some weight or pump out some water, become buoyant, and come up and deliver the ore to the surface. It is very energy inefficient, time taking, and technologically it's very complicated. The idea looks good, but one thing is the devil is in the details, and the implementation is really difficult for this one. So it was tried and it was actually dropped. But as the technology develops and matures, maybe we will have to revisit it at one appropriate time. And the most widely used system is called Gamonod's type system. It's called lifting method. Okay, what we do is that we collect the samples or minerals at the bottom and send them to the mothership using a pipe, or which is called riser actually. This can be a rigid riser, or it can be a flexible riser, or it can be a combination of all. So you can see from the mothership, there is a riser coming down, it's rigid, and later some part of it is actually flexible, and it is connected to the mining machine. So the nodules are connected here, and from here they are pumped to the top. Okay, we have to actually pump it to 6,000 meters height. As you can see, this is actually a typical U-tube. That is, on one side we have a riser system, and the other side of the ocean. So a very little pressure can actually transmit these minerals to the top. But only you have to match the density difference between the slurry, which contains these nodules, and the plain water. But so the geodetic head is minimum in that. But the problem is the friction head. When the slurry goes through this riser, it creates enormous friction that actually creates a very high head for this one. You need high pressure to overcome that friction. And also these nodules, they are crushed and mixed with seawater, and it is made a slurry. Based on the size of these pieces of these nodules, they sink to the bottom. So you have to give a speed which is more than the sinking speed of these nodules. So all these things to be considered while pumping these nodules to the top. That is actually slurry to the top. So there are two kinds of methods. One is airlift method and the pumping method. Airlift method, it's as the name suggests, you have to have a high pressure air source on the ship, and this has to be pumped to the bottom of the riser system. So when the nodules come here, these air bubbles, they make it less dense actually, and then they actually, when the bubbles rise to the top, actually, these nodules are actually transported to the top. Okay, it is easy, it is actually doable for shallow depths, but for depths like 6,000 meters and all, it's a very low efficient system, and over that depths, and we may have to have more openings at different places for actually pumping this air. So it is a slightly a messy system, and it is not as such in this form. It is not used in the underwater mining technology. The next one is actually the pumping system. Instead of having a air from air source at the top, there is a pump at the bottom or in the intermediate places in the riser. So with high pressure, the nodules mixed with the seawater are pumped to the mothership. As you can see, you can use centrifugal pumps or you can use positive displacement pumps. Both have their advantages and disadvantages. But if you want to use centrifugal pumps, it is used to obtain high flow with limited pressure head. So you need number of these centrifugal pumps at different depths actually of this riser. So we cannot use just one single pump. And we should have so many openings for the power supply and the control. And it is actually a difficult system to implement. But in the that Global Explorer, which is a very successful demonstration, they have used this kind of multi-stage pumping. Otherwise, you can use a positive displacement pump, fix it to the bottom of the riser, that is on the seabed itself. These positive displacement pump, they capture the fluid in their chamber, and using the high pressure, they push it to into the riser. So this is a widely used this one, but our calculations show that for almost like a 10% slurry, we need around 120 bar, minimum 120 bar pressure based on the dimensions of the riser hose. We need around 120 bar to do it. And it's not easy to have this kind of pump at the bottom with a power supply. So when we do all these things, we do create some kind of environmental issues. As you can see from this cartoon, the nodule miner collects the nodule, mixes it with seawater, and pumps it to the lift system or riser system. So some kind of plume is generated here, some kind of disturbance is generated here. And in the absence of any currents and all, it takes years to settle it down. And when it comes up also, after taking the nodules, we are going to leave out the wastewater and the trailings. But if it is left at the surface, it may interfere with the, it may create turbidity in the productivity zone here, and it may it may affect the photosynthesis and the productivity here. So it has to be discharged at an appropriate depth. So there is a compromise. And this table here shows that each component of the mining system, what sort of disturbance it generates, where it generates. So we have to make our system environmentally compliant or friendly. So there are now, coming to the international scenario, there are different countries which are sponsoring states and the contractors for the International Seabed Authority. There are multinationals and conglomerates which are working for this one. So generally, Korea, China, Japan, Belgium, EU, and India are very active in the technology development for the PMN. And Russia, Inter-Ocean Metals, Germany, Japan, they are active in the exploration also. And the technology demonstration was carried out so far in USA, Japan, and Belgium, and of course India. So the first and foremost experiment that was conducted using for this mining of the nodules is a Glomar Explorer. It was a covert operation for lifting a missing or sunken Soviet submarine, but the objective was given as mining of the polymetallic nodules in Pacific Ocean. But to their credit, it has been done. They have used huge technology. They have used, we can say metaphorically, used a cannon to kill the fly, but they have demonstrated that it's doable. The technology, technically, it's viable to pump these nodules from these depths. So it was demonstrated in mid-70s. 600 tons of nodules are actually pumped from around 5,000 meters water depth. It is actually south of Hawaii. Korea has done this demonstration, as I mentioned earlier, at 1,300 meters water depth. They have used a propelled mining trawler for this one. And recently, Belgium has taken a lead, actually. Global Sea Mineral Resources, GSR, they have signed a contract with ISBA, and they made a bottom crawler. It's called a Patania 1 and Patania 2, they're called. And they have successfully demonstrated only the locomotion of this system at 4,500 meters water depth. They have not yet collected the nodules, or they have not pumped the nodules to the surface. They are still in the process of collecting the nodules. They are going in steps. But it's a very promising effort. Of course, Nautilus Minerals also made different kinds of systems and all. They in fact had a contract with Cook Island, where the nodules are available in their own EEZ. Later, because of some disputes, they could not go further. And the most successful and the most recent story is Japanese hydrothermal exploration. As you know, Japan is sitting on the ridge itself. So in 2017, they made a tracked vehicle with a cutter and cut these minerals at the bottom. And if I remember correctly, it is a 1600 meters water depth, and they pumped it successfully to the mothership. Japanese agency JOGMEC was very much successful in this one, and this actually gives a lot of hope for us also to move forward. Now, coming back to Indian program, actually, you can take it as a case study. This is the Indian Polymetallic Nodule program in a nutshell. It has 4 components: exploration, environmental impact analysis, mining technology development, and metallurgy development. And metallurgy technology development, that is extraction of these metals. In fact, we are happy to inform you that when these nodules were dredged and brought back, copper was extracted from this one, and sheets were made using this. And there are many byproducts that came because of this the extraction processes. So these are the participating organizations apart from National Institute of Ocean Technology. NIO Goa did a lot of work in this one. Actually, in fact, last 30 years, they have contributed immensely to this program. And IIMT Bhubaneswar is participating in these efforts with their metallurgical processes. And as you can see, when the site was given, it is at 13 degrees south. I would like to tell you that Chennai is at 13 degrees north, and this site is at 13 degrees south, 13 to 15 degrees south. Their survey was conducted, and a first generation mining site was identified here. The abundance was estimated. Average abundance is around 7 kg per meter square at this place. And the best grade where it is available, that also was estimated. A first generation mining site and a test mine site was given to us, where we can conduct our mining tests in future. So the genesis is like this. The preliminary conceptualization of this technology was done in 1990s by different laboratories. But with the inception of NIOT in 1994 by then DOD, the responsibility was given to NIOT for developing mining technology for these deep ocean minerals. And NIOT opted to work on a technology which is crawler-based, self-propelled tracked system actually, with a flexible riser system. This was a conscious decision because we used a flexible riser, which is not a rigid one. If we had insisted on the rigid riser, we would have required a ship with a moon pool and almost with the specifications of a drill ship. So to demonstrate, our motto is to develop and demonstrate the technology, make the industries interested in this one, and then transfer the technology and then hold their hand. With that idea, a flexible riser was actually proposed. So of course, one machine with one riser will not be economically viable, but when it is upscaled, number of mining machines, they can dwell on the sea bottom and they can collect the nodules. Then it will make the operation economically viable. So we are in the process of proving the technical viability before we go into the economical viability. So as like I said earlier, multiple mining machines connected to mother station can be used, and advantages are it is less cost intensive and it's actually modular. So if one system fails, also another system will work. And we thought ease of deployment and retrieval. It is easier said than done because launching a 25-ton equipment in the high seas with a cable of around 40 to 45 millimeters diameter, it's not an easy task really. So when we started, NIOT was very new at the time, so we didn't have any wherewithal to do these experiments. So we adopted a mining machine developed by University of Siegen, Germany. They had a sand mining machine, and it was adopted for the underwater conditions. I can say that whatever ocean technology we learned in the civilian sector in this country, it has origin to this crawler. This we call it underwater crawler. whether it is lights, cameras, navigation, pressure cases, everything has come from this one. Similarly, the sea trials were taken in 1998 and 1999 on board Sagar Kanya for proving the efficacy. One young man is, you can see he's sticking his neck out literally. He was an young scientist at the time, and he's going to retire in this September. He is our director, Dr. Atman. So it shows how far this program has come. And the sand mining was demonstrated at 412 meters water depth on board Sagar Kanya in the west coast of India successfully. But by the time in 2002, a 15 years contract was signed with the ISBA for eventually demonstrating the mining at PMN site in Indian Ocean. So we adopted our technology for that one, and we converted the sand mining system into a nodule mining system by putting an appropriate nodule pickup system, you can see here. But the problem is that we don't have, our machine is actually capable of going to 500 meters water depth. There are no nodules at 500 meters water depth. So what we did is that we prepared the nodules, artificial nodules, which have properties similar to the real nodules, laid them on the sea bottom, and then we sent our machine for harvesting them. This was successfully done in 2010 and 11 at around 500 meters water depth. And this was a actually huge confidence booster for us. No other country has demonstrated an integrated system like this at these depths, except for Japan, of course, at 1600 meters water depth. Then, now we want to venture into, after demonstrating at 500 meters water depth the capability of locomotion and nodule collection and pumping to the surface, we want to graduate into 5000 meters water depth. But before we go there, we have to analyze the sea bottom. We have to analyze what is the strength of the bottom to withstand our mining machine, whether we can get any locomotion on that one. We used to collect the seabed samples or soil samples and test them on the surface, but we could never get a true reading. So we wanted to make an in situ soil tester, which can go down to that depth and do the soil testing there. So we made this system which can go up to 5500 meters. We launched it, and on the right hand side corner you can see the mining, this is a soil tester in the nodule field penetrating the sea bottom. We successfully measured the soil strength there, and as you can see from the graph, we got the shear strength, and we got the bearing strength also of the soil. Now we have got enough data to size our machine and to design our machine, and to explore the water column actually at from surface to 5500 meters water depth. We made a remotely operated vehicle. It is actually a work class with a robotic arms, sonars attached to that one. And this machine has been developed. You can see the specifications on the screen. And it has been used around 45 times beyond 1000 meters water depth. And it was used twice at polymetallic nodule site and one at the polymetallic sulfide site. But a lot of work is to be done using this one. It's a machine. It's like a microscope. Once you see it with a telescope, what is there, you can send it, you can concentrate on a fixed area, and you can get a high resolution survey of the bottom. So this probably will be doing it in the year 2021. So this is how it looks like on our own technology demonstration vessel Sagar Nidhi. You can see cable, a specialized launching and recovery system, and ROV here. And you can see the containers in which we sit and we operate the system at the bottom. So now we have seen the water column. We have examined the bottom. Now based on this data, we set about now designing our mining machine with the following specifications, with a target of collecting around 8 tons per hour with this thing. And we had a concept actually, and we started from the drawing board, and slowly we moved on to the real, actually, the fabrication of this machine. This machine, when it is launched on the seabed, it has to it encounters a lot of forces like traction force, bulldozing resistance, soil displacement, water drag and all. So we have to give enough force to overcome all these things for this machine to move forward. So we estimated all these things, and then we fixed the specifications of the system for developing. So after developing the machine, how do we launch it? There are different ways of launching. There is called configuration and handling studies have been carried out. And after analyzing different kind of configurations, we arrived at actually something called a VHF system. And this is how it looks like. From the ship, mothership, we lower it actually at around 5,500 meters. There is an intermediate pumping station which is hardly below about 200 meters above the seafloor. This mining machine moves, collects the nodules, crushes the nodules, mixes them with seawater, using a centrifugal pump pumps it to the pumping station, which is 200 meters above the seabed. From there to 6,000 meters top actually to the mothership, it is pumped using a positive displacement pump. So we have divided the critical systems into ship-based systems, water column systems, and the sea bottom systems like this. And I cannot talk about all the systems as that because of the paucity of the time. We can see that the vertical riser, a hose is actually tested. It needs to have a capacity to withstand around 120 bar internal pressure. So we tested that one. The pump system is separately tested. The traction and the locomotion is separately tested in the bentonite tank, which has similar properties of the seabed. With all these things now, we have assembled or fabricated our crawler. And now this has to be lowered from the top, and it has to be controlled from the top. You have to give power, you have to give the control signals, you have to get the data, and we have to drive it on the sea bottom. For that, we made electronics for that, and we made a containerized control room where we sit and control this mining machine. And also, what sort of power is required for operating this pump and this mining machine? Our estimate clearly shows that we need around 550 kilowatt of power, which has to be supplied through an umbilical cable, which has fiber optic fibers going through that one, conductors going through that one, and Kevlar for actually giving the strength to the rope and all. And we are in the process of identifying this umbilical cable and a specialized launching and recovery for system for this one. So this is how it looks like when it is done. Actually, when the crawler is assembled, as you can see in 2019, we have tried this locomotion at in May 2019. So we are going in steps. First, at 890 meters, at 65 meters and 890 meters, this machine was tested, and you can see how it was launched, and you can see the underwater pictures. You can see the track marks and how the soil was destroyed by this this mining machine. It was successful at 890 meters. The next phase was that it was done very recently in February 2020. At 3,000 meters, this mining machine was tested. This weighs around 15 tons in air and around maybe 7 to 8 tons or maybe 5 to 6 tons in water. This is how actually it is launched from the ship. And before just launching, you can see how it looks like. There is a short video of our works. Maybe at the end of the talk, I'll be able to play a 2-minute video for you. And I have not talked much about the environmental impact or the metallurgical processes because I am sticking to the technology development alone. But before we demonstrate our technology or our test mining system at CIOB, that Central Indian Ocean Basin, we need to collect the environmental data before, during, and after the mining machine trials. So we are working closely with the National Institute of Oceanography for collecting this data, analyzing this data. And these are our future plans. We have divided our work into small steps at a time. The first one is to demonstrate the locomotion at this 5,500 meters water depth. Second is nodule collection capability and efficiency estimation. Third one is separately pump these nodules which are already extracted and maybe taken in a basket to the depth and demonstrate the pumping capacity, and finally integrate all these systems and demonstrate a end-to-end system at 5,500 meters water depth. And that we are hopeful that we'll be doing it in 2024. And just I didn't talk much about metallurgy. So you can see the sheets made of cobalt, copper, and nickel extracted from these nodules dredged. They have not been brought by mining machine, but they were dredged using the some kind of dredging techniques. It is so IIMT is actively working on this one. So these are the vehicles that actually, these are the offshoots or actually spin-offs of this thing. We made a mining system which can go to 6,000 meters. We need a deep water ROV. We made a deep water ROV which can go to 6,000 meters. And there is a soil tester which can go to 6,000 meters and test the soil strength in situ. And there's a drill which can be used for gas hydrate exploration. I am not going into that one now. And there is this shallow polar ROV which can work in 500 meters water depth, which can work in polar conditions also. In fact, it has been demonstrated at Antarctica also. So these are the spin-offs of the Indian deep sea mining technology development program. And the next step is, there are some limitations about unmanned vehicles actually. If ROV has limited range and AUV has no control. If you combine the capabilities of these two, actually that is manned submersible, three scientists can go to 6,000 meters water depth in a small submersible which has an endurance of around 12 to 16 hours and which has emergency endurance of 72 hours further. So we started this project actually. It's called the Manned Ocean Mission. So we have identified what are the critical technologies involved in this one, and with the help of Indian industry and ISRO of India and also some international collaborations, we are in the process of actually developing these components. By probably 2024, this Indian manned ocean mission, that is Samudrayan, this Matsya 6000, this vehicle will be able to demonstrate its capabilities. And these are the, we have already visited many of these places shown on the globe, and these are the places of interest for us actually for minerals and for geological purposes and all. We have been working in these areas and we would like to work more in these areas. So I would like to summarize my talk because I think we are approaching the time, and this, it is no doubt ocean is a treasure trove of strategic minerals, and as the depletion of terrestrial mineral resources is a fact, we cannot ignore ocean mining option. And technology is maturing, and several nations and conglomerates are developing these technologies, including India. There was a misconception, and actually there is a misconception that India is not in the forefront. But through this webinar, let me assure you that no, India is very much in the forefront. And in fact, ISBA is looking forward for India to demonstrate this technology at 5,500 meters water depth. And but whatever technology we should develop, it should be economically and environmentally also viable. And we, at this juncture, our motto is to develop and demonstrate. I think that we have done and we have been doing it. Now it is a high time that industry is sensitized about the need of this technology, and we have to make them participate in this venture. So we have to, there are many E's involved: expertise, equipment, environment, ecology, and economy. These are the buzzwords we cannot forget. And I would like to conclude my talk saying that there is something called Gartner's hype cycle. So when an idea actually is generated, it gets a lot of hype, and media also joins in. So it's at the peak, but after some time the negative press starts. So there is actually a peak of inflated expectations, a trough of disillusionment is there, and later the technology matures and slowly it goes up. In my view, we are at this phase, that is slope of enlightenment, and the success is only around the corner. and very soon there will be a mature technology for safe harvesting of ocean minerals from the ocean depths. I could not cover a lot of topics because of the paucity of the time and because of my own limitations. But there is a wonderful book actually compiled by Dr. Rahul Sharma of NIO, ex-NIO Goa scientist, and who is who of Indian mining program, renewed stalwarts of the program, Dr. Sudhakar and Dr. Baban, Dr. Nagendranath, Dr. Das, Dr. T.R.P. Singh, Dr. Atmanand, and yours sincerely, and so many people. I might miss some names. They all have contributed to this book, and it makes a wonderful reading. And in its time, it was one of the most downloaded books, if I am right. So you can get it from the internet, and it makes a good reference book for the people who want to work in this mining technology development. And it is clearly said that the impossible is indeed possible when talented engineers with the courage to take prudent risks are provided an incentive to stretch the state of the art. This is actually a statement of the Hughes Glomar Explorer expedition. And with this, I thank the organizers for providing me this opportunity to talk to you. And if any questions are there, I'll be able to take them. Thank you.
Thank you, Dr. Ramadass. That was a very informative talk. There are a few questions from audience, and I have posted it in your chat window. So kindly read the question and answer.
Yeah, I'll take 2 minutes if they can see me on the camera. Actually,
sure.
I would like to show them something actually for the interest of the audience. Yeah, am I visible?
Not yet. Yes, yes.
You can see what I'm holding here is the polymetallic nodules, which took some millions of years to form. And you can see there is a shark tooth here. Around this, it is nucleated. So this is how the nodule looks like. Actually, this is taken from the that is actually more polymetallic nodule site in the Indian Ocean. And also, I want to show the effect of the pressure there. If we send a thermocol glass like this, actually container like this, because of the triaxial pressure, actually it is compressed to this size. So that is the effect of the pressure there. So whatever technology we have to make, it has to be really made for working at that kind of very difficult conditions there. Okay, right. So now can I access my chart window for the questions? Yeah. Yeah, the first question is about will it affect to the natural geological process like seafloor spreading and composition of surface, oceanic crust. This is actually because if you see the area that is really affected by this mining, when compared to the size of the ocean, it's a very small area. So of course there is some kind of it will be disfigured. The sea bottom will be disfigured. You'll be taking out something. But many of these minerals are two-dimensional minerals, especially polymetallic nodules. Actually, except that you just collect them and you disturb the soil, you don't do much disturbance there. Whereas cobalt crust and for the hydrothermal sulfides, you will have to do some kind of scrapping and take the thing down. But when compared to the terrestrial mining, the effect is very less. And that doesn't create any kind of either tsunamis or any that kind of hazards to the coastal states and all. That is minimum. Only thing is the disturbance that is created that may last for several months, if not years, for it to settle down. And there is now megafauna there. I'm sorry, biologists should excuse me if I'm wrong, but there is not much megafauna there. It's only a microfauna is there. And the disturbance is, in my view, minimum. But anyway, environmentally, we should be very conscious and we have to attend to these things and make the technology really environmental friendly by causing the most minimum possible disturbance there. The second question is it possible to use submersible for sediment coring? We can have, can we send some vehicle having corers? Can we precisely get the undisturbed cores? Yes, we can do it actually. With ROVs, remotely operated vehicles, we send some push corers, not actually very, they cannot go to the hard material and all, but push corers we send, and we get the, I cannot say completely undisturbed cores, but we can get some cores. But there are underwater drills. Actually, NIOT has that drill, which can go up to 3000 meters water depth and take a core of 100 meters. We can say it is an undisturbed core. We can take the core. We have that capability. We have proved it recently to 1000 meters water depth, and we have taken around 60 meters core below the seafloor. Yes, this can be. That's also a kind of underwater vehicle only, so it is possible. And third question is, instead of towed ship-based platforms, is it viable to make it oil rig type platforms to harvest? Yes, it is possible. In fact, the Glomar Explorer, it is a sort of a drill ship only. So we can convert a drill ship for this one. But it won't tow. It actually, it sends some vehicle down, and the vehicle moves down on the sea's bottom, collects the mineral these things, and then mixes it into seawater, and using a riser, it is pumped to the thing. But we can use this drill ship for this purpose. Then another question is, what is the scope of the career of an ocean engineering student? And what is the chance that India will start investing more in this sector? In my view, there is actually a great scope, because we have to look at the oceans, and now the government is also really very intent on blue economy, developing the blue economy. So when you are looking at the oceans for the future, and we want to generate a good percentage of GDP using these oceans, then definitely ocean engineering students have a good role to play in that one. But it is not limited to ocean engineering students alone. If you are good at your field, it's electrical, electronics, mechanical, structural, whatever field of engineering you are, you can contribute to the development of ocean technology. And the last question is, any cost-benefit analysis had been done in deep sea mining? Any private enterprise shown interest in the commercial exploitation? Actually, the commercial exploitation has not been allowed by the International Seabed Authority. Only the exploratory mining is allowed. In fact, India is participating in these discussions, and India has contributed richly to these discussions in formulating exploitation code, which may see the light of the day in a year or two. After that, these commercial operations will be allowed. And as I told earlier, we have to sensitize the Indian industry about the potential in the deep sea mining. So the best way to do it is demonstrate it first, and then share the results with them, and then sensitize them and make them a participant to this one. But in my view, without private enterprise, and it is almost impossible for the commercial exploitation of these nodules. Thank you. And if any more questions are there, they can be sent to me by email. I'll be able to answer. If I don't know the answers, I'll consult my colleagues, and I'll be able to answer these questions. So I once again thank the organizers, the Ministry of Earth Sciences, especially IIT in Pune, for all these arrangements, for all their patience with me. Thank you for your attention.
Thank you, Dr. Ramadass. Thank you for answering the questions. So we can go offline now.
Yeah.